If you try to second power z squared plus az plus b, something like that, then you get this when you plug that f into this equation. You get this, right? And if you try z to the third power, so z cubed plus az squared plus bz plus d, you'll get something like this. Now these polynomials have been very well investigated in pure mathematics by the pure mathematicians, independently of quantum physics. In fact, as is often the case, quantum physics or physicists have taken the mathematics already discovered by the mathematicians and just used it in their theories about physics. Now that's pretty much been the case for a couple of centuries, since after Newton. I mean, Newton was such a genius, I mean probably the greatest physicist who ever lived, that when he was as good a physicist as a mathematician, when he did not have the mathematical techniques to do his stuff, well, he just invented them. I mean, he just invented calculus to solve a physics problem effectively. Now, recently, there's another fairly young, still not old, mathematical physics genius. His name, alive today, his name is Ed Witten, and he has problems in string theory. He's basically a quantum field theorist, very interested in string theory, made enormous contributions to that subject. When he has problems with his string theory, he invents the math. And he's done that so successfully that the mathematics community have given him the Fields Medal. The Fields Medal is sort of like the Nobel Prize of mathematics until the recent creation, starting 2003, the Abel, A-B-E-L Prize. Abel was a Norwegian mathematician, a very early pioneer of finite group theory. See my previous lecture course on finite group theory if you're interested in it. Alright, anyway, so these polynomials are called Hermite polynomials, or if you like pronouncing it in the French way, and I speak French, Hermite, right? If you're going to pronounce it in the French way, the H is silent, the ER is a sort of an air, like hot air, very appropriate for the French, right? Hermite. So Hermite or Hermite polynomials, right? And now I can go back to this equation. This equation is called Hermite or Hermite equation. That's his equation, right? And he analysed it, and it has lots of properties, interesting properties. So the various solutions to this for higher values of z to the n, higher order polynomials, you get these. And so these are called Hermite or Hermite polynomials, right? Derived from Hermite's equation. Now, quite a few people have worked on these polynomials. For example, that would be h0, h1, I guess, h2, h3, and so on. Now, hn in general, they can be generated. These polynomials, the sequence of them, can be generated by using this formula. If you want to know where that came from. Now, this is a case of physics using mathematics. So the mathematicians have been working on Hermite polynomials, well, since Hermite, right, for several centuries. Okay, now, since your wave function is of the form f of z, where f is a polynomial, satisfies Hermite's equation, so the wave function is proportional to an f, that's your big F, but f is a Hermite polynomial, right? Times e to the minus z squared over 2, right? So that is your wave function. Now, you don't know, it's proportional to, so if you make it a constant, you need to normalize it. You need to normalize this thing to find what that constant is. And to do that, it's you need to know more about the mathematics of M-eat polynomials. And there's a whole bunch of questions in the exercises at the end of the chapter, well, actually at the end of the book, but this chapter 4's exercise, and a lot of them this time. So doing this kind of thing is in the exercises for the chapter. And for general n, so energy n plus a half, for general n, so with your nth M-eat polynomial, your constant, to make this a constant here, not just proportional, your constant's quite complicated. But it can be found. This alpha here is just short for square root of m omega over h bar. But look, you've got a square root inside a square root. It's non-trivial, right? So there's the wave function for the harmonic oscillator at energy or eigenvalue n. Right? There's the general case. And to get that, you need to know various properties of M-eat polynomials. And to get familiar with that, you need to solve the exercises. So I'll probably do some of this in the problem-solving part of this lecture in another session. All right? Okay. So if you've got this wave function now for the general case for n, what does it look like? So you could plot the wave function. In fact, well, what they're plotting here is not the wave function, but the probability density. So in other words, just the square of this, and plotting it versus x. Now for n is 0, you just get a sort of bell curve type picture, right? Sort of. Here's your x, the distance that it's oscillating from the 0 point, the middle point. Okay. Now for n is 6, you get something more complicated. Looks a bit like this. And for n is 12, you get a whole bunch of oscillations. But the general pattern of the oscillation starting to look like the classical case. So this dotted line here, that's the probability distribution of the classical case. Now you may remember from the previous session, we actually calculated that, because now we can compare. So as n goes large, the quantum behavior begins to approximate the classical behavior, and that kind of thing is called the correspondence principle. So as n goes to large, then the quantum version of the simple harmonic oscillator approximates, behaves like the classical version of the simple harmonic oscillator. Okay, right. I got a sort of heavy bar now. As usual, run out of board. Well, I always have to. Now a kind of new topic, sort of. It's still obviously on the topic of simple harmonic oscillator, but it's a very elegant, very practical, very useful alternative way to analyze the quantum simple harmonic oscillator. And essentially the technique uses certain operators. Well, different authors have different labels, but a common one is they're just ladder operators. Like climbing a ladder, you go up one rung at a time or down one, so you're climbing up one step or going down one step. So another label is like step up operator or step down operator, and you'll see, well, it'll have to be the next session, but you'll see why these particular operators are labeled that way, why they're labeled like a step operator or a step down operator, or collectively, generically, just ladder operators, right? So you can do this for yourself. Somebody dreamt this up, I suspect by the mathematicians first, because this technique reminds me of something in Lie algebra, those of you doing first year math Lie algebras with me will see this kind of ladder technique used, and that was invented by the mathematicians around the turn of the century ago, and quantum mechanics didn't start using this till many decades after, so I assume again the physicists, mathematical physicists, took these techniques from pure math. Anyway, so you can rewrite your simple harmonic oscillator STI, Schrodinger's time-independent equation. You can rewrite it in this form, okay? And you've got like A minus and A plus as times your wave function. So this is now an operator. So you've got an eigen equation, right? Here's your operator, here's your eigenfunction, and here's your eigenvalue. So it's written here in the form of an eigen equation. Bit of revision. Go back a few lectures for the concept of an eigen equation. All right. Now this A minus and A plus. How's it defined? Well, A plus is defined as d by dz minus z, and A minus is defined as d by dz plus z. And you may ask, well, so what? Well, you'll see next session that by using these operators, A plus, A minus, something gets stepped up and something gets stepped down, and that's where these labels came from. But you'll have to wait for the next session to see how this stuff works. But it's very elegant. It's sort of much easier than this kind of stuff, and very, very practical. So till next session.